Hi everybody, welcome back. This is the second part of the decision making chapter. We're going to be talking about decision making with certainty, sort of, and heuristic processing. So when we think about decision making with certainty, we have a question because nothing is ever for sure. But when people are making estimates about the probability of something occurring, they tend to rely on certain base rate parameters, or they ignore the base rate parameters. Here's an example of people making a decision about whether or not they're likely to be sick. So in the Valley area, which is Phoenix, where I'm from, it's reported that 1 in 10,000 people per year will contract meningitis. And this was actually something that happened about 20 years ago. There was a bunch of meningitis going around. A free test is available, and it's pretty good, 90% accurate. So you go to get tested, and the test comes up positive. What is the likelihood that you really have meningitis, and how worried should you be? So if everybody thinks about that in their head, how worried would you be? There's a way to actually test this, which is called Bayes' theorem. So Bayes' theorem calculates probabilities. And so in this case, you would calculate the probability of being sick given the accuracy of the test. So whether it's a 90% accurate test or a 95% accurate test, when you look at the probability, it's pretty small given the base rate. So you don't have meningitis. However, as you start using a more reliable test, a 99% accurate test, now you still don't have meningitis, but it's starting to look a little more suspect. If you repeat that 99% accurate test again, now it's looking more and more like you have meningitis. When finally you do it a third time, it is likely that you have meningitis. You are that 1 in 10,000 people. So the idea is that people do not use base rate information when they're making decisions like this. So with a more accurate test, you can see with a 99% accurate test that is then repeated 3 times, it becomes more and more likely that you are the person that has meningitis. And by the time you get to the third time of taking this test, it looks pretty likely that you're the one with the meningitis. So what we know from these sorts of studies is that people have a tendency to ignore base rate information, like the 1 in 10,000 people. In this current example here, Traversy and Kahneman did what was called the CAB problem. So I'm going to read this to you, and I want you to think about the information that I just provided with regard to base rate information, meaning 1 in 10,000 people had the meningitis. You have to go through a lot of tests to find out if you were the one. So here's this scenario. One night, a taxi cab was involved in a hit-and-run accident. 2 cab companies, the green and blue companies, operate cabs in the city. 85% of the cabs in the city are green cabs, 15% are blue cabs. An eyewitness has identified the cab that hit the pedestrian as a blue cab. The court tested the witness's ability to identify cabs under appropriate visibility conditions. When presented with a series of green and blue cabs, he was 80% accurate. What is the probability that the guilty cab involved was actually a blue cab? So think about what the answer would be for a second. If you put this information into Bayes' theorem, you can see that most people would say 80%. And they often say that because that was the number of identifications that he got right when making the decisions about the cab. However, people ignored the base rate that there weren't that many blue cabs to begin with. So you can see that if you look at Bayes' theorem, the likelihood is 0.41. And people don't really update information either. You can give them the new information and they tend to ignore it. So there are a lot of experiments looking at this, whether it be medical decisions, judging contests. Here's another example of where people don't really use Bayes' theorem. Linda is a 31-year-old, single, outspoken, and very bright woman. She majored in philosophy as a student. She was deeply concerned with issues of discrimination and social justice and participated in anti-nuclear demonstrations. So which is more likely? Linda is a bank teller or Linda is a feminist bank teller? So think about that for a second. Here's another one, and I'm going to give you the answers to these at the same time. Jack is a 45-year-old man. He's married and has 4 children. He is generally conservative, careful, and ambitious. He shows no interest in politics or political issues, and he spends most of his free time on his many hobbies, including carpentry, sailing, and mathematical puzzles. Jack is in a room with 100 people, 30 of whom are engineers. The probability that Jack is an engineer is, I'm hoping you said 30%. A town has 2 major hospitals. The larger one delivers 700 babies per day. The smaller delivers 200 babies per day. On any given day, about half the babies are boys and half are girls. One day, one hospital delivers 60% boys. Is either hospital more likely to experience this event? Think about that. And so here's the answer. In the Linda problem, she is more likely to be a bank teller because you cannot be more likely to be part of a smaller group within a larger group. So there is no way she's more likely to be a feminist bank teller and also be a bank teller. It's more likely just to be a bank teller. So the fact that people might jump to the conclusion of feminist bank teller is called a logical impossibility and a conjunction fallacy. And people jump to those sort of conclusions based on stereotypes. The Jack problem is that people considered the chance of Jack being an engineer to be at 70%, but we know that it's 30% because there were 30 engineers in a room of 100. And the hospital problem, this is something I want you to think about. The smaller the denominator of a fraction, the more likely you can move the probability around. So if it's a small hospital and you have a few more baby boys, you are more likely to change the overall percentage than if you have a large hospital and have a few more baby boys. Hopefully that makes sense. So the question is, why do people commit these errors? Is what they do is they put a lot of faith in small samples, like a heuristic process, which is using a stereotype, and they skip other information such as base rates or other information that's presented to them. So this is actually called the representativeness heuristic, meaning that because Linda seems like a feminist or Jack seems like an engineer, you put more weight in that assumption. Representative of that particular category. Another heuristic is called the availability heuristic. So it's the idea of how easy something comes to mind. People will jump to conclusions about that. So probably at the age you're at, a lot of people are getting married these days, and so you feel like everybody's getting married. When everybody's not getting married, just the friends of yours you can think of quickly come to mind, and it feels like everyone's getting married. That's the availability heuristic. So Kahneman and Tversky tested this, where they gave people a list of names. Half were men, half were women, and half of each of those names, depending on the condition a person was in, was celebrity names. And so later on, when they asked people to determine whether there were more male or female names in their list, they tended to misremember and put a lot of weight on the celebrity names because those names came to mind easily. And therefore, if there were a lot of celebrity names in their list that were male, they had a tendency to say there were more male names, even though the male and the female names were the same number. Another thing to be thinking about is what's called anchoring and adjustment. So it means that when people estimate something, they make some sort of guess. That creates a mental anchor. And then new information should allow a person to adjust that anchor. However, people are not really good at doing that. An example would be Kahneman and Tversky actually did a study where they had people spin this roulette wheel and they ended up with some number between 1 and 100. And then they asked them to estimate how many African nations were in the United Nations. And people based the number that they guessed of the number of African nations in the UN on the number that was spun on the wheel, which nothing was related. It's just, it kind of gave them an anchor. And I want you to think about a real world example. So if you've been privy to a request for a donation, oftentimes there will be something saying a minimum requested donation of $25 and then $50 and $100, and then there's other. And you feel really bad if you give less than $25 because that is sort of the threshold that is given to you. Similarly, I want you all to think about this particular scenario. And this is one of Kahneman and Tversky's classic studies. Mr. Crane and Mr. T were scheduled to leave the airport on different flights at the same time. They traveled from town in the same limousine and were caught in a traffic jam and arrived at the airport 30 minutes after their scheduled departure times. Mr. Crane was told his flight left on time. Mr. T's was told his flight was delayed but left 5 minutes ago. Who is more upset? And pretty much everybody knows that Mr. T's was more upset. And the reason why? Because he just missed the flight. Just missed it. So it makes him more upset. For college students, it's like you're more upset if you miss an A by 1 point than if you miss an A by 20 points. And that's all.